right, so I think we've got about a quorum now. So for those of you who are here a little early, we were talking about kids and that sort of thing and interruptions from kids. So in order to not have this last too late for those of you who are affected by that, it gives me great pleasure to introduce today's colloquium speaker, Andrew Houck. Andrew was an undergraduate at Princeton University and then got his doctoral degree from Harvard in apparently just 5 years, which is great. Something to aspire to for all the grad students here. And then moved on to a postdoc at Yale, and now is a member of the electrical and computer engineering department at Princeton. Where he has done lots of great works, in particular applying circuit QED things to study problems beyond just simple engineering of qubits, applying to new fields. And so I think that's what he'll be focusing on in today's colloquium. I'll just mention Andrew, of course, has won a number of awards and prizes. He was a Hertz Fellow, he was a Packard Fellow, and has continued on breaking in the accolades with good reason. And so I'm very excited to hear the latest from what's going on now in your lab. So I'll turn it over to you now.
Great, thanks for the introduction. I will attempt the always fraught moment of screen sharing. All right, can people see everything?
Yes.
Good. Okay, so I think I'm going to focus sort of broadly on the work going on in my group. And I would say, you know, we do some things in quantum computing, we do some things in quantum simulation and looking at fun physics with the pieces of quantum computers. And what brings me the most delight about the work I get to do every day is the fact that I have this enormous breadth of topics that I get to consider. And so today's colloquium, I'm actually going to focus sort of broadly on this entire stack of disciplines that intersect with circuit QED and talk a little bit about how they all come together in the work in our lab. And so, you know, it starts, you know, if we think about superconducting circuits in this whole range of disciplines, it always starts something very simple. If we have a superconducting circuit and we want something that has some particular well-defined energy, the easiest thing we can do is we can make an LC oscillator. An LC oscillator has a particularly fundamental frequency. You can think of it as a harmonic oscillator. We have some number of photons that live in it, in our case, microwave photons, and we can represent it by a Hamiltonian. Well, I guess if we have one oscillator, it's just a dagger A. If we want, we can also make a non-linearity. We can make our photons interact, if you like to think of it as interactions, or you can make something that looks more like an atom by replacing the inductor with a nonlinear inductor. This nonlinear inductor goes by the name of a Josephson junction. And in the sort of typical limit that we work in, where the charging energy is much less than the Josephson energy of this junction, this really just looks like a slightly softened harmonic oscillator where you have some number of photons living inside, but the energy level spacings get just a little bit closer together as you move up the ladder. And you can think of this as an effective photon-photon interaction, or you can think of this as an artificial atom where you can isolate the lowest two states. Now, if you want to build a quantum computers from this, what you really care about is how long you can get superpositions to live in this kind of system. And if we look at sort of 20 years of superconducting qubits, we've actually done quite well for ourselves. So the first superconducting qubit debuted in 1999. It had a lifetime of about a nanosecond. And for more than a decade, we saw some exponential Moore's law-like growth in how long these macroscopic objects could hold a quantum coherent state. That progress really stalled around 100 microseconds, maybe a decade ago. And we haven't seen as much lately, but we have seen some real growth in the complexity. Everybody's heard that Google has at least claimed to be able to do something that's hard to simulate with a classical computer on their quantum computer. IBM is also regularly building 50+ qubit systems. They look sleek and fancy and unlike the things you typically see from an academic group, but they're really just these qubits sort of hooked together in larger and larger grids. But if we want to move to the era where we can do more interesting things with these computers, either quantum computing applications where we actually build computers or study interesting fundamental physics, we need to keep the progress going at the fundamental device level. And so for the first part of my talk, I'm going to talk about how we combat noise in these devices, how we can keep superpositions alive longer to push us towards this error correcting threshold. This also enables much more complex and powerful quantum simulations and enables us to address and realize more interesting physical systems from a fundamental physics perspective. So if you think about this, what are the sources of noise, right? We have a superconducting qubit. This is a large object. These things are typically 100 microns across. They're susceptible to all kinds of things: charges, magnetic fields, photons, dielectrics, cosmic rays. There was a really fascinating paper from Google recently that showed you can see the impact of a cosmic ray that causes catastrophic errors in their machine about once every 10 seconds. Radioactivity, quasars, all of these things can couple into the system and destroy these kinds of fragile superpositions that we build. So if you want to go about and try and build something that lasts longer and can maintain sort of more complex quantum coherent states, you generally have 3 strategies you can adopt. And I think of these as sort of the turn the volume down, put the earplugs in, or wear the noise canceling headphones, right? So turning the volume down is really about reducing noise. And that means understanding material science, understanding how the properties of materials couple into your system, being able to sort of improve how you build them. And it's really an intersection with that area. You can also do the earplug approach. You say, well, I don't really care if there's noise. I'm going to build qubits that are insensitive to particular sources of noise. And this approach really involves understanding Hamiltonians and how particular symmetries or properties of Hamiltonians render you immune to noise. And finally, there's the well-known sort of quantum error correction, which is actually actively monitoring for errors and applying corrective feedback. Though that requires you have all of these first pieces to be good enough that you can do that. And that's something that really nobody in the world can actually do to any great benefit right now. Okay, so we're going to start by thinking about reducing noise in materials. So you could ask this question: how long should a qubit live, right? You have this object is really quite large, but it's made of superconducting metal that's lossless. We have sapphire substrates, and sapphire is a nearly lossless substrate. If you dig up the literature from the 80s and look at, loss tangents in sapphire, you can see that even in the worst crystals people measured at low temperature, you can make Qs of like 10 to the 8th, which would be like a 30 millisecond lifetime. And in the better crystals people have made, you can get up to a second. This is orders of magnitude better than the best qubit ever made. So what's the problem? Well, there's this quote: God made the bulk, this surface was invented by the devil, and it's particularly true for quantum devices. So it's been known since the mid-2010s that surface properties matter quite a bit for quantum devices. If you take this capacitor here, which comes from these 2 blue pads, and you just move them further apart, less of your electric field lives in the part of the dielectric near the surface. And as you do that, the quality factor of your device goes up. And so you can sort of see that, in fact, if you look at the participation ratio, the fraction of the energy of your electric field that lives in the top 3 nanometers of your substrate, that really, the quality factor depends on how much of your electric field is there. This is really smoking gun evidence that surfaces matter. And so we actually teamed up with some material science folks at Brookhaven National Lab to try and understand the various kinds of surfaces and interfaces of our materials, right? So these are often relatively simple materials. It's niobium on sapphire. And so you have 2 different interfaces that you might worry about. You have the metal air interface where you have oxides. And niobium actually has, if you do XPS, quite a thick layer of this sort of amorphous niobium oxide that's not the NB205 that you want. And so this sort of rather thick amorphous and sort of ill-defined oxide layer is quite bad. And if you look at where the metal meets the surface of the substrate, you can actually see that, while the metal has some regular order and the sapphire looks absolutely beautiful, this sort of 5 nanometer layer at that interface is quite disordered. And so we were talking about this with a physical chemist at Princeton, Bob Kava, and he said, well, obviously you should not be using niobium. He studied niobium back in the early 90s, and it has just an incredible range of complex oxides. And some of these are insulating and some of them are superconducting, and you can't really control which ones you get. So he suggested we use tantalum. It turns out that tantalum is not something that's easy to grow in its normal crystalline phase. So in bulk, tantalum is a BCC crystal, but if you grow it in thin film, it forms a hexagonal phase, which has a much worse superconducting properties. But if you deposit it hot, you can actually get this near epitaxial growth with relatively large grain sizes. And if you look at the interfaces we care about, the sort of non-stoichiometric oxide almost vanishes in tantalum. So you get a much thinner and much more stoichiometric oxide, and the interface between the sapphire and the tantalum matters is quite a bit better. You can see that you almost have perfect oriented, or you have oriented growth, and you have almost perfect epitaxial growth where the tantalum tries to orient on top of the oxygen. And when you put all this together, you can see, in fact, a 3 to 4 times improvement over the state of the art, including all of the sort of commercial qubit manufacturers. And so this really shows that this sort of academic science-driven approach, where you really try to look at the material's properties and understand physically what's going on and correlate that with coherence, can give you significant improvements. Here I showed this plot earlier, which showed sort of a compendium of all of the coherence times in the field as a function of participation ratio. And then sort of moving up this blue curve is our process development. And now we're sort of hovering 4 to maybe even 8 times better in some cases than the state of the art. And this work is really progressing. And this is in collaboration with Natalie De Leon's group at Princeton and Bob Kava, and of course, some collaborators at Brookhaven National Lab. And this shows how sort of one flavor of research, really understanding material science, can help improve these quantum devices by really digging into the dirt. Now, what I'd say I'm sort of probably is where my core strength lies, is really understanding this sort of Hamiltonian and circuit development. So can you develop a circuit that's insensitive to noise? Okay, so what's nice is these improvements are multiplicative. So if we get some improvements from materials, that's great. But if we can also render our devices immune to noise, then that's also good. And this is what we did back in 2005 when I was a postdoc and helped develop the transmon qubit, which is the one that everybody uses. We learned that if you increase the EJ to EC ratio, you get this exponential suppression in the dispersion of your bands as a function of your gate charge, which renders you extraordinarily immune to fluctuations in that gate charge, which give you much longer T2s. This is why the transmon is the qubit of choice in industry. But the states, as I said at the beginning, look really just like harmonic oscillator states. And harmonic oscillator states have quite large matrix elements that connect any transition that's not forbidden by parity rules. And so if you encode your qubit in these bottom 2 states, then it's actually quite easy for your qubit to decay from the first state to the ground state, which makes T1 energy loss, often by these material absorptions I talked about in the first part of the talk, the dominant source of noise in these systems. So in the transmon, you have absolutely no T1 protection, but you have T2 protection. We also know ways that you can get T1 protection. So if I make a double well potential and I make the barrier big enough, then I can have one state that lives in the left well and one state that lives in the right well. These wave functions have disjoint support. So one is 0 and the other one is non-zero. And this means that the matrix element is sort of essentially exponentially suppressed depending on in this barrier height. And so you have exponential protection against T1. But when you isolate the states in these distinct wells, then usually this double well picture for a flux qubit is a function of flux. And as you change the flux, you tilt the well. This means that your energy difference between the 2 states is not well defined, and you have a significant amount of dephasing. And so you have to pick your poison. You can sort of get some intrinsic protection versus T1. You can get some intrinsic protection versus T2, but you can't get both at the same time. And so if we were to build a real qubit wish list, what we would want is we would want a new qubit that has disjoint support for our states, that the 0 state and the 1 state live in different parts of phase space. And you would want, as a function of the control knobs, the dispersion to be extraordinarily flat to exponentially suppress any kind of dephasing. And you really want both of these things at the same time. And this is the thing that nobody has actually been able to realize. So if you think about one way you could get that is if we had a magic device that allowed us to have four electrons tunnel at a time. So double Cooper pair tunneling. So if you had a double Cooper pair tunneling device, some device that allowed you to do this, then as a function of, without a flux loop, as a function of phase, you would get a double well potential. So here there's no loop that would allow you to sort of introduce dephasing, and you could get the same kind of protection you get by having sort of qubits that lived in the left well and right well. And so this loopless double well potential is the thing that essentially is the holy grail of protected qubits, because you get T1 and T2 protection. And over the years, there have been a number of theory proposals about how you might possibly be able to get there, but all of them have generally involved extreme parameter limits or unconventional superconductors in ways that have never quite panned out. And so we tackled one of these devices, which is a bit based on this design that Getayev proposed called the 0-pi circuit. And the idea is to try and build a circuit that essentially simulates this 4-electron tunneling. And the circuit looks something like this. So it's a pair of Josephson junctions, a pair of capacitors, and a pair of inductors. And you want an incredibly large inductance that there's a very high impedance along this sort of bottom and top path, and a very large capacitance across these sort of diagonals, which means that there's a very low impedance here. And what happens if that's the case is when one Cooper pair tunnels across, say, the left junction, it builds up charge at this sort of, a charge imbalance across this top and bottom node. And that builds up charge on the sides of these capacitors. And so there wants to be the opposite charge on the other side of these capacitors. Now, if this inductor weren't here, if this were just sort of one sort of continuous piece of metal, what would just happen is, this negative charge would just happily sort of move onto the other plate of this capacitor and everything would be fine. But this impedance is really large, and so this can't happen very quickly. And so the fastest way, the easiest way to sort of put the proper charges on the opposite panel is for a second Cooper pair to tunnel across this other junction. And so if you treat this sort of top node and this bottom node collectively as a mode, then what you get is always correlated Cooper pair tunneling. And this gives you your effective 4E tunneling event. And this gives you effectively the double well potential that you want, which you can then use to build a truly protected qubit. So this is what we do. It turns out that that is in fact the case, but in a more complex circuit, you also have structure in the other direction. So you get this double well potential, but within each well, you get a rather rich spectrum of states. Still, if you choose your parameters properly, you can get the 0 and the pi well to have no loop that controls the energy difference between these. This would give you a fairly robust coherence. There is a loop in the other direction which controls this other degree of freedom. So you're only actually first order protected against flux noise. And the states that live in these wells are disjointly supported. And so you wind up getting or expecting incredibly long T1s. You can also see that the states here really look more like artificial atoms and less like, pure, just slightly messed up harmonic oscillator states. And we actually can really, start to think about doing some real atomic physics in these sort of more complicated qubit systems. So we build this device. Here's a sort of fancy sort of drawing that Jens Houck, my theory collaborator, made. So it consists of two capacitors that are sort of at these opposite ends. These are these blue and gray things. It's very important that you have no or minimal stray capacitance between the blue and gray at opposite ends of this device. Then we have the two Josephson junctions shown here in this green area, and the inductors are created with these 200 Josephson junction arrays, which effectively form a superinductor. And when you build this system, you can actually measure the spectrum of it, and it looks incredibly complicated. But if you just put on our modeling parameters, you can actually fit almost every line in this spectrum to a known transition. And it's this diagonal line down here and here that is the fluxon transition, the one that involves moving from the 0 well to the pi well. That's the one we really hope to use for our qubit. But if you actually look at the data, that line doesn't show up at all. And you might be troubled by the fact that the most important line doesn't show up at all until you remember that we designed this qubit so that you in fact can't have a matrix element between those particular states. You can't drive that transition. And so if you attempt to drive that transition, you'll see nothing. And that is, in fact, the protection that we talked about at work. But what you can do is you can use a Raman process. You can drive up to, in our case, it's the 13th level, which is the first level. It's the one right here. It's the first level that has it has weight in both wells that allows you to do a Raman transition. And so you can drive up and over from one well to the other. And when you do that, you can see that we have, in fact, incredible T1 protection. And our T1 has gone all the way up to 1.5 milliseconds. And it's maintained a relatively high degree of coherence in terms of T2. With this, T2 is currently limited by, we believe, thermalization. So the attenuators in the fridge heat up when you drive this qubit. And we have some strategies that we're working on right now to get this to be much better. We expect we can get this T2 number up quite a bit. We can also bump this T1 up quite a bit, given that it's really exponentially sensitive on parameters. But this is really the first and I think only device that has true T1 protection and a very strong protection against at least first order flux noise. Now, this is just scratching the surface of the qubits that are available. If we think about sort of the things that have been protected or things that have been proposed that are protected qubits in this space, I've sort of drawn a bunch of circuits here, and this is the qubit we made here, but this is a qubit proposed by the Devray group, as is the fluxonium molecule. There's another qubit proposed by Lev Yoffe's group, and we don't really have an understanding and a systematic method to explore these larger circuits. And so I think where we're really going is we're trying to think about, is there something more like a periodic table for superconducting qubits, some real deeper properties here that we can exploit to find new protected qubits. Because although we've tried quite a few qubits over the 20 years that we've had superconducting qubits, the primary trajectory of qubits includes, is essentially a Cooper pair box, which is a lone Josephson junction, the Transmon qubit, which is a Josephson junction shunted by a capacitor, the Fluxonian qubit, which is a Josephson junction shunted by an inductor, and the newest qubit, heavy Fluxonium, which is a Josephson junction simultaneously shunted by a capacitor and an inductor. So there's really very little that's actually been explored in this space, and the amount of space here, especially as we think about sort of qubits that fulfill particular roles or have particularly interesting atomic properties for quantum simulation, for instance. There's really just an incredibly rich tapestry with which we've only barely begun to work. Okay, now, the third way that you can really sort of move beyond errors is with this active quantum error correction. This is really to monitor for errors, apply corrective steps, really do fast gates, fast feedback. And this involves sort of a huge amount of system design. I should say this is building the bridge to this post-NISQ era, to this era where we can do noise correction is really one of the chief goals of this Co-Design Center for Quantum Advantage. This is one of the 5 DOE and National Quantum Initiative centers. I'm currently deputy director of the center, and this is really one of the chief efforts of that center. And so this is where I hope that we collectively with our 20-some partner institutions are going to be going over the next few years. But in the meantime, what do? Well, if you're in industry, what you do is you say, just forget about that. We'll put a big X through that, and we'll invent the NISQ era of quantum systems. And from an industry quantum computing perspective, what that means is, you run algorithms and they're exponentially decaying as a function of the number of gates you do, but you try and do as much as you can. If you are, an academic like me, what it means is you say, well, we have these, these incredibly sort of coherent pieces for quantum computers. We have resonators and we have qubits, and we can build them into larger and more complex systems. And instead of running sort of, arbitrary algorithms, let's use these to study really interesting bits of fundamental physics. And over the years, we've actually put these together to study a sort of a very large number of things that fall under the sort of rubric of quantum simulation or many body quantum mechanics. We did this dimer experiment where we saw a dissipative phase transition. We have this sort of this other phase transition in an array of 72 qubits. qubits. We've built 2D lattices and have a scanned probe that kind of plays the role of our quantum gas microscope. We've looked at bound states and spin boson problems in these ultra strongly coupled systems, which are really exciting. The work that I want to talk about today is really trying to build up particularly novel lattices. So rather than just building a 1D grid or a 2D grid of qubits, what are the kinds of things you can do if you can actually build arbitrary systems? Because one of the exciting things about superconducting quantum platforms is that we can actually build really quite arbitrary structures, right? We're only constrained by what we can possibly draw. And that really gives us, a complementary set of things that we can study to, say, traditional cold atom simulators. And I'm really interested in trying to exploit the versatility of these systems to look at different kinds of many-body physics. And so today I'm going to really talk about unusual lattices, or this is sort of how do you decide what to make? If you can make anything you can draw, how do you decide what it is you actually want to make? And it's this pathway that led us into for us a very mathy turn. And so I want to talk about that a little bit, because again, what really delights me about this field is that we've gotten to draw already on electrical engineering and material science, but also sort of physics in our Hamiltonian design and understanding coherence properties. And in these many body physics experiments, we've done quite a bit of really interesting physics. But we also get to sort of draw on graph theory and math to try and help us understand how to relate the structure of these lattices to the energy spectrum and their physical properties. So we're going to go back to where we started. We have our lone harmonic oscillator, but now instead of one, we're going to make two. If we have two coupled harmonic oscillators, then this can realize a tight binding like Hamiltonian, where excitations in one harmonic oscillator can hop back and forth to the other harmonic oscillator. And so this realizes a tight binding Hamiltonian. Physically, we often don't have real inductors and capacitors. We build these in terms of transmission line resonators. So a transmission line resonator is just sort of a long wire that's about a wavelength or half a wavelength long, and the frequency is determined by the length. You can model it as series inductors and parallel capacitors, but really it just looks like this. Typically, we have these coplanar waveguide resonators, which have a center pin in the middle. This is something that's like half a wavelength long. These capacitors you can think of as mirrors, and you can think of this as a Fabry-Perot style cavity. And if we want to have two cavities or two lattice sites for our photons, then we just take two of these coplanar waveguide resonators and we capacitively couple the endpoints. And this is what gives us the hopping. And so the energy of each lattice site is determined by the length, and the hopping is determined by the capacitors very locally at the endpoints. We can build systems up from here. So we can take our transmission line resonators, and what's nice about these is that we can sort of bend them, and as long as the total length is the same, they all have the same energy. And so we can build an enormous array of resonators that have essentially the same energy and the same properties. And this flexibility is what allows us to build things that are difficult to build in other ways, because we can decouple the distance between lattice sites from the hopping to different lattice sites. At the endpoints, we put capacitors. We can not only have capacitance to one other resonator, we can have capacitance to multiple other resonators. So from these pieces, we can, for instance, build this lattice here, which turns out to be the Kagome lattice, where every resonator can hop to every other resonator. So each squiggly thing here is one particular lattice site. And then we have these coupling capacitors, which determine the hopping Hamiltonian, or the tight binding Hamiltonian for this system. Now, what's really special about these resonators is that we can really define the physics entirely by the graph. So if you have a regular lattice of actual real atoms versus a disordered lattice, well, these atoms, these particles have some sort of cloud where they live, and the hopping between neighboring lattice sites really is going to depend on the distance between these lattice sites. So if you change the distance between neighboring lattice sites, you're also changing the hopping. And so this picture on the left would realize a regular tight binding graph. This picture on the right would realize something that looks like a disordered sort of square lattice, where everybody can hop to their nearest neighbor, but the hoppings are not equivalent. And what is particularly useful about these superconducting circuits where the hopping is entirely determined at the endpoints is that we can decouple the spacing between our lattice sites and the hopping rate. So we can build a lattice that is essentially disordered in terms of its physical spacing, but has even hopping. And from a Hamiltonian perspective, or from a graph perspective, these two graphs on the left are identical. And so it allows us to really define everything by the graph. And from there, we can start to build all kinds of interesting things that you can't ordinarily build. And so the first thing that we built a few years ago with my postdoc Alicia Kolar at the time, now she's a professor at the University of Maryland, is to think about building things in curved space. So in flat space, everything sort of works the way you expect. You can have hexagons, you can tile the hexagons, you can build a lattice. But if you have, for instance, fewer sides on your polygons, if you have 5-sided polygons, then you can't tile them sort of regularly in physical space. There's this gap here, they're not big enough. But if you distort the pentagons, you can in fact tile in spherical space. But in order to do that, distance is not preserved. For hyperbolic space, the polygons are too big. So here I'm looking at heptagons. But if you make them smaller as you go away from the center, you can actually realize a graph in a 2D plane that is a tiling of heptagons. But again, distance is not preserved. But with our superconducting lattices, we can actually absorb that sort of non-preservation of distance into the shape of the resonator. So we can actually stretch or bend the resonators in order to fit more or less resonators. So we can actually realize both spherical and hyperbolic space on a 2D planar chip by distorting these lattices. And so this really gives us a way to look at very exotic lattices. Even though distance isn't preserved, the hopping is preserved and the graph is preserved and the Hamiltonian is therefore preserved. And so we started looking at different kinds of lattices we could build. So in particular, the most natural lattice, and I'll get to this in a little bit, are these Kagome-like lattices. And for a Kagome lattice, if you just look at numerically all of the eigenvectors for these lattices, what you get for the Kagome lattice is you get a flat band at -2, and then these dispersive bands. You can actually calculate the band structure for the Kagome lattice quite easily. It turns out that for these hyperbolic space pictures, you can't calculate the band structures anymore because you no longer have block waves. Translations no longer commute in hyperbolic space, and so the typical pictures you're used to seeing of band structures, just there's no way to actually calculate them, and it's actually an ongoing challenge to think about what the band structure might look like in hyperbolic space. It actually relates to quite a few really important mathematical problems. So mathematicians are very interested in trying to think about how you might think about block waves in these hyperbolic spaces. But you'll also notice something else interesting, which is that the flat band that exists in the Kagome lattice is not gapped, it touches the other bands. But when you go to the heptagonal band or the nonagonal band, this gap appears between your flat band. Now, flat bands are really exciting because any arbitrary degree of interaction can give rise to many-body physics. They often have topological properties. There's really quite a bunch of physics that relates to flat bands. And so when we saw these flat bands that we could get that were gapped, we were particularly excited. So we decided to try and build these are with the localized states like that. So we decided to try and build, in particular, this heptagonal Kagome lattice. And that's something that we could lay out and actually do. So you see here, this is a picture of our device we made. This is a heptagonal Kagome lattice. So it's a tiling of heptagons in a Kagome geometry. It contains 2 shells. So it has, I think, 140 resonators. Operating at 16 gigahertz each, and we can measure the input output, and we can see quite a good agreement between sort of the theoretical band structure that we expect and where we actually see transmission from this thing. And so we can actually start to build these non-Euclidean lattices. And that's one direction that we're going. But if I just go back here, we were also really interested in these flat bands. And so once we saw this flat band that had a gap, we started probing as to why the flat band sometimes has a gap and sometimes doesn't. And is that related to Euclidean versus non-Euclidean geometry, or is that somehow related to this line graph property? And so what is a line graph? So If we go back to this picture I showed at the beginning, the way we made this 2D lattice, and this is the very first 2D lattice we ever made. And when we built it, we were like, aha, we're going to make a hexagonal lattice. We like this lattice because 3 resonators come together at one point. We can make sure that the hopping from every resonator to its neighbor is symmetric. And so we can actually do really very interesting, we can actually ensure that there's relatively low disorder. And so when we first made this, we thought we were making, graphene. We thought we were making a hexagonal lattice. But you have to remember, these lines here are the resonators. They're not actually the typical things you see in a crystalline graph, which are the bonds. And so there's a resonator on the edge. There's a resonator, and each resonator is an edge on this lattice. But those edges are actually the lattice sites. And so really, to think about what tight binding model we've realized, you actually have to put a lattice site on each of those edges and connect the edges that share an endpoint, because that's where you have hopping. And so this lattice that we realized is actually the Kagome lattice, which we get by drawing hexagons. And so we call this graph here that we draw the root graph. And this graph that we get is mathematically the line graph. So it's what you get by putting a point on every edge and connecting edges that share a vertex. And this line graph property is really what's going to give rise to these flat bands, and it's going to help us figure out when we get gapped flat bands. So we can think about lots of different line graphs that exist. So you can have graphene, whose line graph is the Kagome lattice. You can have these sort of heptagonal graphene, which gives us the Heptagon-Kagome lattice. That's the thing we actually realized. Trees in math have been a really important point of study for these. And then there's the square lattice, whose line graph gives us this leaf lattice. If you look at the band structure correspondence here, you can actually look at the band structure, for instance, of the square lattice. You can see you get these sort of typical sinusoidal bands. And if you look at the band structure of the line graph, what you see is that it's in fact identical, shifted up by -2 with a flat band at -2. The same for graphene. If you look at the band structure of graphene and the band structure of the Kagome lattice, the band structure here is now shifted up by -1 with a flat band stuck at -2. And so there really is a band structure correspondence that holds between any graph and its line graph, any regular graph and its line graph. And it's this that we're going to exploit to figure out what we might actually want to build. So the idea is you can think about the Hamiltonian for the root graph, the thing we actually draw, or you could think about the Hamiltonian for the line graph. This is the Hamiltonian, the thing we actually realized. And to figure out what's going on, you can think about all of this, by the way, is in our mathematical physics paper, which is, now we've gone all the way from dirty materials to mathematical physics, which is given by this incidence operator, which is a matrix which has a 1 if an edge and a vertex are incident and a 0 otherwise. So this incidence operator basically takes us from the graph to the line graph. And so it's an operator that moves from edges to vertices and back. And so you can think about what the operation of this operator does on a particular site. So for instance, suppose we start on a particular lattice site and we apply the M operator. What that does is that gives us each of the 3 incident edges to this one vertex. That gives us 3 edges. And now if we apply M dagger to these 3 edges, what we get is we go back to, we get all of the things that are incident on these edges, all of the vertices that are incident to these edges. So we get these 3 vertices, plus we have 3 ways to go back to our original point. And if you look at what this is, well, these 3 vertices are actually the nearest neighbors of our original vertex. This is what you get if you operate with the actual Hamiltonian, plus you get 3 times the identity matrix. So M dagger M gives us a diagonal matrix, which along the diagonal has the degree of the vertices, and plus the actual Hamiltonian. This is the thing that allows you to hop to your nearest neighbors. We can do the same thing for MM dagger. So if we start with a single edge and we apply M dagger, we get the 2 incident vertices. And then if we apply M to that, we get the neighboring edges. These are the neighboring points of the line graph, because remember, in a line graph, every edge is actually a lattice site. And we get 2 times the identity, because there's 2 ways we get back to where we started. So we get 2i plus the Hamiltonian of the line graph. And in fact, what you can show is that these are where the correspondence comes from. So because of these relations, you can show that every eigenstate of m dagger m has a corresponding eigenstate of m dagger. That is, every eigenstate of dx plus hx has a corresponding eigenstate of 2i plus hs with the exact same eigenvalue. So these have an eigenvalue correspondence, and that tells you that the eigenvalues of the line graph have to be the eigenvalues of your original graph minus 2 plus the degree of each vertex. And this is why the graphene lattice shifted up by 1, because that's a degree 3, and the square lattice shifted up by 2, because that's degree 4, and everything else is in the kernel, so everything else sits at minus 2. And so this allows you to sort of show that every line graph is going to give you a flat band at minus 2. And the question of whether or not it's gapped is really a question of, does the original graph realize, does the original graph actually realize its minimum possible eigenvalue, which is the thing that will be minus 2 when shifted, because the minimum possible eigenvalue of this is minus d. And so does this realize the energy minus d or not? And it turns out you can prove that if a graph is bipartite, there is always a state that is at energy minus d. It's the one where you just color everything +1, -1, +1, -1, +1, -1 throughout. This will always have the energy minus d, which means that your flat band will never be gapped. And in fact, if your graph is non-bipartite, you can't have this state. And that's the only thing that can give you minus d. And so therefore, it has to be gapped. So in the end, what that says is the line graph of any non-bipartite graph will always be gapped. And so you can come up with all kinds of Euclidean non-bipartite line graphs that give you gaps. In this paper, we prove that there are ways to actually find maximal gaps to make the gaps as large as possible. And these are things that we've started implementing and are really interested in studying. But there's one more question you can ask if you want to now go back into physics, which is, are these gapped flat bands topological? Do they have some interesting topological properties or not? And so you can go about and think about how you can sort of show that these are topological. And the way you need to do that is you actually need to count the degeneracy of that flat band. And that's relatively easy to do. So if you think about our root graph, it has some number of lattice sites per unit cell, in this case 2. That tells you the number of bands. The line, and it has some degree, how many vertices each vertex is connected to. In the line graph, the number of edges is nd/3. It's the number of sites per unit cell times the degree over 2 because you double counted. And that tells you the number of bands, because every edge in your original unit cell becomes a point in your line graph unit cell. And so you can go from the sort of properties of the root graph to the properties of the line graph. Now, every band in the root graph gets translated up to the line graph. So all of these 2 bands get shifted upwards, and all the other bands have to be flat bands. And so the degeneracy of the flat band is nd/2 minus n. It's the number of bands in the line graph minus the number of bands in the root graph, which is in fact the number of edges in the root graph minus the number of vertices in the root graph, which you can actually relate to the number of faces in the graph. So there's really all of these geometric things come to bear on this problem. And it's gapped if the root graph is non-bipartite. So when we ask, are they topological? There's sort of a number of things you can do. So one way is you can just sort of exhaustively try and figure out, can you find any of these graphs to start with, right? So if we want a degree equal to 1, then that means we want n times d minus 2 equal to 2. And you can just look for integers n and d that can solve this equation. And there's only, in fact, 2 pairs of integers, and none of them give you non-bipartite graphs. So you can show that there are, in fact, no non-bipartite graphs that gives you a non-degenerate flat band in a line graph. That's provable just by doing this. For d equals 2, you can actually do the counting, and you can show that there are in fact 2 pairs that give you gapped flat bands. And then for each of these pairs, or each of these things, you can actually just use topological quantum chemistry to figure things out. The second way you can actually do this, and this is the way that my postdoc, Christy Chu, has been pushing, is to actually prove universal rules for the topology of the line graph based on the properties of the underlying graph. And so what we have a really good understanding of is what the compact localized states look like in these graphs. So what does it look like? What are the states in this flat band? And in particular, in an even-sided polygon, it's always these even-sided loops of alternating sign that give you the flat bands. When you have that, then what happens is you can't hop off of this sort of closed ring, because you always get a destructive interference from the -1 and the +1 trying to hop off. But going around the ring, 2 things that are next nearest neighbors will always hop on to their nearest neighbor and give you this eigenvalue of -2. And so you can always find these sort of closed loops. You can also find these extended states, which are the things that are of interest if you're interested in topology. And so what we do, and in this talk, I don't have time to walk through the whole process, but I would point to this paper that Christy wrote that really describes this in detail, is you want to calculate the real space invariance. And what that means is you think about where the sort of maximum Wyckoff positions in your crystal are, where the points of high symmetry are, and then you contemplate what happens when you apply your symmetry operators around those maximum Wyckoff positions, and you can see what kind of eigenstates you have. By adding up all of these eigenstates, you can actually figure out the real space invariance. These are sort of essentially a counting of how many of which kinds of eigenstates around which Wyckoff point you have. From that, Andre Bernig's group has worked really hard on this topological quantum chemistry, where the real space invariants give you essentially the band representation and whether you have something topological. Now, here we're not going to have anything that it has stable topology, but we're really interested in fragile topology. What Christy has been able to show is that the properties of these eigenstate counting are entirely determined by essentially the number of even and odd faces and the space group symmetries of your underlying lattice. And so now we have a constructive way where if you want to build a lattice that has interesting topological properties, we know what the symmetries you need to realize in the underlying root graph are, and then you can realize the line graph, and from there you can build your lattice. So for pure line graph lattices, there is exactly one and only one lattice that has fragile topology, and it's this triangle line graph of a triangle lattice. So that's exciting. But if you're willing to take some of these higher degeneracy lattices, there actually is fragile topology that's sort of spoiled by the higher degeneracy of these lattices. So if you add in a perturbation like a C2 preserving perturbation, then you can maintain all of the properties we needed to get there. So here is an example of one of those lattices. You take your unit cell, you can see that if you look at the Wilson loop binding, there is no windings, there is no topology. But if you take these lattices and now you add one C2 preserving extra hopping. So you add an extra hopping to these lattices, then suddenly you can create things that are fragile topological, essentially by splitting off some of these extra bands and revealing the underlying topological states. And so these are things that we are now in the process of building. This is sort of really the thing that Christy has been pushing. And here you can find all of these different lattices and really enormous families of lattices that allow us to realize interesting topological states. And so we are trying to build these by essentially building new kinds of resonators that give us these kinds of shapes. And so here you need Y-shaped resonators and X-shaped resonators. So we no longer are dealing with just simple linear coplanar waveguide resonators. We need to be able to couple more things than just three. So we need these six-way couplers, and we need some new ideas on how to actually demonstrate that these are topological properties. And again, this is something that Christy has really pioneered. She's now demonstrated nearly all of these different kinds of resonators and is building up these even more elaborate Hamiltonians than the things we demonstrated, for instance, with the hyperbolic lattice. Okay, and then of course, in all of this stuff, you know, if you want to have interactions, we can couple this to qubits, and that lends a nonlinearity of the system. And then we can look at small amounts of interactions. And so in addition to the ongoing experiments trying to build these fractal topological states, we're also looking at what happens when you have one or many sort of strong couplers that allow us to have interactions in the systems. So I hope that gives you a flavor of at least the sort of more mathematical side of things that we get to deal with. And I just want to conclude and leave some time for questions by just reminding you of sort of the breadth of things we talked about. So in the beginning, I talked about building tantalum transmons and how that gives us a factor of 3 or 4 in coherence over sort of all other transmons, and even including industry groups. This was really a massive team effort. Alex and Leela were the students who led this project. The 0 pi qubit is the first qubit that is protected both against T1 and T2, at least the first order. This was really led by Andras and Pranav. And Andras is going to continue doing protected qubit work with his new group at Colorado, where he'll be starting in the fall for people who are looking for students and postdocs, or places to do graduate school and postdocs. Alicia Kolar really led our work on hyperbolic lattices and line graphs. Alicia is continuing to do some of this really interesting work at the boundary between quantum simulation and math at her group at JQI at the University of Maryland. And then all of the topological work and really trying to implement these topological lattices has been led by my postdoc, Christy Chu, who is not yet a faculty member, but will likely be on the market this fall, also a DAMOP thesis prize winner and fantastic person. So I just throwing that out there. Okay, thanks everybody. And I'm happy to take questions.
All right, thank you very much. Everyone feel free to unmute yourselves and give a big round of applause. Thanks for a wonderful talk. We have plenty of time for questions. So I think the easiest is probably to either unmute yourself and call it out if there's a moment of silence, or if not, if there are a lot of people who have questions, maybe raising hands or posting them in the chat is also fine. I'll monitor those things and pass them along. So maybe I'll get us started with a question. So you talked about building these, non-standard lattices that didn't host block waves. And how big of a lattice, is maybe even general for the repeating lattices, how big of a lattice do you need to actually build? How many sites do you need to build to capture accurately the properties of regular, simulate an artificial material.
Yeah. So I would say, in the Euclidean lattices, it's actually not that big, right? Like you get quite a bit of the flavor of these with a dozen unit cells, I would say, and that's easily done in 100 resonators, and doing 200-ish resonators is generally not much of a problem for us. You start to run into sort of parasitic modes when you go up to thousands of resonators. But even these relatively small lattices start to realize the physics. It's a much more complicated question for the hyperbolic lattices. And there really, how you terminate the boundary becomes quite important, right? And this is sort of fundamental to hyperbolic lattices, right? So the boundary is always a fixed fraction of your volume. So if you have a sort of finite truncated lattice and hyperbolic space, your boundary and edge effects are always going to be important. That's in some sense what makes them interesting, but it also, you know, makes questions of, you know, well, how big is enough to capture this problem, you know, these properties, you know, it makes it a little bit, it depends on really what property you want to ask. Now, you can also start thinking about trying to put in periodic boundary conditions, right? So we can actually start to try and route these things back onto themselves. It gets a little bit complicated to do that in a way that, you know, you don't have to worry about the length of your resonator. So you probably have to start building some multi-layer structures. But it does let us really start to look at some of these sort of curved space pictures of materials, even with this, you know, few shell construction.
Thanks. All right, so there are a couple of questions in the chat. Maybe I'll go in order of posting, or actually I'll invite Noah. Do you wanna say your question, or should I just read it off? All right, so what would you like to say about first year physics and math education if someone gave you a soapbox, which I'm now doing?
Why, I'm glad somebody asked. So one of my other big passions has been physics and math education, and really revising our first year curriculum at Princeton in a way that tries to engage with more modern topics, with applications, finding new ways of teaching similar materials, and sometimes jettisoning some material that has been traditional. I would say the most important thing I would say, though, is to really believe in your students, honestly. So we built an entirely new curriculum after noticing that we had a significant achievement gap in our first year performance. So students who had less calculus just dropped out of the School of Engineering at like 3 times the rate of students who didn't. This also meant that we saw significantly higher rates of attrition in underrepresented minorities compared to average, and also with women compared to average. And this had persisted for quite a long time. And in devising the new curriculum, we said, well, you know, like that seems like it's on us and not on them. So there has to be a way that we can teach better. And with this revised curriculum, we actually saw the attrition rate of students who had not had significant calculus preparation go down from about 25% to about 8%. So we saw a 3-fold decrease in the rate of students leaving the School of Engineering, and basically a closing of the performance gap between different groups coming in. So I would say, 1, believe in your students, and 2, you know, think about new ways to teach the same content, because sort of doing the same thing over and over and lamenting the outcome is generally not something we would ever do in labs. So it's not something we should do in teaching. Soapbox done.
All right, so in the interest of time, I'll just read a couple other questions that have come up. So this is from Xiaoyu Wang. So can you comment on the flux sensitivity of your 0 pi qubit compared to the normal flux-based qubit with double well potential, which can also be protected to flux noise to first order at the sweet spot?
Yeah, that's a great question. So the flux qubit can be protected to first order at the sweet spot, but where are we? But if you are at the sweet spot, if you are, okay, so the way you get T1 protection in the flux qubit is you have states that live in the left well or the right well, right? So that's where your T1 protection, there's no overlap between these wave functions. If you move to the sweet spot, then you get a first order insensitivity to flux noise. But what happens at this sweet spot is your eigenstates are now the symmetric and anti-symmetric superpositions of these 2 states, which actually now have overlap and a real matrix element. So at the point where you become T2 protected in the flux qubit, you lose your T1 protection because you no longer have this disjointness. In contrast, in the 0 pi, the flux loop tilts you along this sort of long axis. And so it tilts you sort of from this sort of local, essentially from this blob here to this blob here, but it doesn't mix your 0 and pi well. So that means that you can simultaneously be at the flux sweet spot, which gives you these symmetric and anti-symmetric superpositions you see in the pi s plus and the pi s minus states. Those are the symmetric and anti-symmetric superpositions. That's what gives you your first order flux insensitivity. But your other eigenstate, you're not encoding information between these two states and worried about T1 between them. You're actually encoding information between the zero well and the pi well. And so then you don't have that sort of T1 effect.
All right, so one other question in the chat. This comes from Debadri Das. Can we initialize arbitrary nodes in these lattices to simulate a specific network?
Yes-ish. Whether or not you can and the degree to which you're able to do that is really a question of how many wires you want to put in your fridge and how many resonators and qubits you have. And so as we are building lower cost, higher number of channel devices and bits of control, which we've been really working on in collaboration with a bunch of people at Fermilab and Dave Schuster's groups in these RF socket-based devices, then you can imagine really building much more complicated control. I think this is a problem sort of generally in the field of academic quantum hardware, where you're really limited by the number of wires you can put in your fridge a little bit, but also just by the number of generators you can hook up to those wires. And these new sort of direct synthesis FPGA based generators are going to dramatically change what we can do even this year. I think they're really starting to come online. And so I think there's a huge amount of stuff that we can do there.
Thanks.
All right, so another question that popped up in the meantime. So what type of numeric, this is from, apologies if I butcher your pronunciation, Iken Kokabas. What type of numerical tools or methods do you use to model the dynamics of qubits in these novel lattices?
Yeah, so you can do a whole bunch of different things. So if it's one of these novel dynamics of qubits in these novel lattices. Okay, so for these novel lattices, if you're really putting in interactions and building the lattices to be hard, it's everything grinds to a halt quickly, right? So generally, the linear lattices, we can look at the dynamics and the eigenstates just with sort of brute force numerics on stuff that we write ourselves in Python, once you turn on interactions, then things get difficult. And so we'll often just model very small systems sort of with brute force numerics or try and figure out sort of approximations that are valid in the larger systems. And that becomes quite a challenge, right? And I would say one of the challenges in all of this is that these are fundamentally open quantum systems, right? So our particles are photons. Particle number is not conserved. We can look at, for instance, steady states of damp-driven systems. We can try and stabilize systems, but we're now really looking at these sort of custom open quantum simulators. One of the reasons that they're fun is that we don't always know the answer we're going to expect. When I take on new students and I explain the sort of quantum simulation versus the quantum computing halves of the groups, I tell them, they're both really the same. We're building large superconducting circuits and we're poking in microwaves and we're looking at what comes out and we're trying to see what happens. But in the computing side of the group, surprises are bad, right? We generally have a model of exactly what we want to have happen. And anything that deviates from that is almost always like things are just way worse than we hoped. And in the quantum simulation side of the group, we have these lattices that we have all of these tools that tell us that, there's these topological properties and they're interesting for this reason and that reason. So we're not just like blindly shooting in the dark. But we also don't always know exactly the answer we're going to see. And often we are surprised, and those surprises are the ones that are good and exciting. And so, what you want to do really depends on your personality and whether you want to sort of, be seeking after a goal where you know the answer, or, have a strong hint that something is going to be exciting and just have to see what the actual dynamics are going to be, because we can't really do the full numerics in advance.
All right, so are there any other questions? All right, if not, let's thank Andrew again for a great talk. Yeah, thanks.